Hello everyone, here's a video on alkyl halides, nucleophilic substitutions, and the latter half of it will be on elimination reactions. So in a introduction to substitution reactions, we have everything will have an electrophile and a nucleophile in the reaction. We know the nucleophile always has a negative charge if it has a charge. So in this, the nucleophile is the iodide, the electrophile is the alkyl halide, and in this, we know the only atom in the T-butyl chloride that is reactive is the center one, the one with the bond to the chlorine, because it's the only one that we have something on the carbon that we can do anything to. A carbon with a bunch of hydrogens we can't do anything to, so it's just that carbon-chlorine bond, and that's based on the electronegativity of the chlorine and the ability of it to have a pull on the electrons in that bond between the carbon and the chlorine. So the first thing we need to do is talk about nomenclature of halogenated organic compounds. Here we have the 2-bromo-2,5-dimethylheptane, so we need to start where the bromine gets the lowest number and the alkyl group's the lowest numbers possible. We've named some of these before, but we remember that fluoro, chloro, bromo, iodo, that's when it's out as a substituent off of the molecule. We could also, like I said, up here at the top, the T-butyl iodide, if we can name the alkyl chunk, we can make it a functional group off of the iodine ending. So here we have a 1, 2, 3, 4, 5. So it's a pentane. So on this pentane, we have a 2-bromo-3-methyl pentane. Okay. On the next one, we have 2, 3, 4, 5. We could number it either way, with one being on the left or one being on the right. When we look at this, we know it is a 5-carbon base, so it's a substituted pentane, and when we have an alcohol, we drop the E and add OL, so it is a substituted pentanol. Now, since it's a pentanol, we changed the base name, so the alcohol has to have the lowest number, so it has to be a 2-pentanol or pentane 2-ol. And in front of that, we have a 3,4-dimethyl 2-pentanol. Okay. A primary halide is one with one R group on it. A secondary halide has 2 R groups on the carbon containing the leaving group, and a tertiary one has 3 R groups on the carbon containing the bromide. Okay, so primary carbon, secondary carbon, and a tertiary carbon are there. And those will be very important in this chapter because the different reactivities of the molecule depend on what we have. Now, we have in the past talked about the possible mechanisms for a free radical process and the different steps of it, and we've done this already, so we won't talk through these again. If you need to look at these, look back at the videos for the free radical reaction. Okay, they're all written out here. We have the initiation. Okay, everything has that, and everything has a termination reaction, and then in between we have either things relating to a double bond, which would be 2 and 5, and then 3 and 4 are relating to abstracting a hydrogen and replacing it with a bromine on just an sp3 hybridized carbon. So 2 and 5 go together, and 3 and 4 go together in those mechanisms. So we know the mechanism for the free radical coronation or bromination, it doesn't matter which one. In this, the one we usually use in class is with bromine-bromine instead of chlorine-chlorine bond, because the bromine free radical is much more selective in how it does things than the chlorine one. but either one works, and we have to be careful that we draw the right arrows. They're all fishhook arrows with one point on, one hook on them, instead of the ones we've been drawing so far with the double hook, because the double hook is implying 2 electrons move, whereas the fishhook is implying 1 electron moves. So be careful. This mechanism, we only use it when we have bromine and light or something else that has a, as we talked about back in chapter 4, has a bond that can homolytically break. So it has to have the exact same thing on both sides. So the bromine, bromine, the peroxide, oxygen, oxygen, you know, things like that, that can split in half and have 2 of the exact same thing. If we don't have that, it's not going to be a free radical process. And here are some of the choices and what we can do with it and all. And this is really just a repeat from chapter 4. So I was going to skim through this pretty quickly in where we put things on. We know that in the free radical process, the free radical itself is electron poor, so it wants to go on the most substituted carbon of the molecule. So that's the key to it. And a chlorine isn't near as selective. That's why in this bottom one we get a 60-40 ratio of the isopropyl chloride and the N-propyl chloride. Okay. If we do that with bromine, it's a 97-3 ratio, so it's much more selective in how it does things. And in this bottom part of this page, it really shows that we don't get any of the primary bromide. It's all the tertiary bromide when we use the 2-methyl propane. So all we get is this one, so we don't have to worry about any of the side products. That's why bromine is the one we'll use primarily in class. So here, with the bromination of a cyclohexene or any alkene that has hydrogens on the adjacent carbon to the alkene, the allylic carbon, okay, we end up getting the bromine abstracting the hydrogen off of the allylic carbon, and that's because once we form this radical, we can draw resonance structures for it, moving the radical around. So the allylic carbon, that allylic radical, is much more stable, and the allylic is spelled that way. Okay, so that radical is much more stable, so that's the one that's going to form, because in all of these reactions we're going to form the most stable intermediate possible. So here is 2 examples of a reaction. If we just have hydrobromic acid, okay, we end up with the bromine adding to the more substituted carbon, because we know HBr is an electrophile. And so if HBr, the strong acid, is the electrophile, we know the alkene has to be the nucleophile. So all that's going to happen is well, better draw it down below. We'll draw it twice. So in this, oops. The alkene goes and grabs a hydrogen from the HBr, and it's going to give us either of the following 2 possibilities. It's going to give us with a positive charge on the more substituted carbon, or the positive charge on the less substituted carbon of the alkene that was the alkene. Okay, and we all know that cations, the more substituted they are, the more stable they are. So this one will not form, will only form the more substituted one. So we form this out of as a possibility, and then once you have the cation, the bromide can add to that, and that gives us the 1-bromo 1-methyl cyclohexane. Okay, So that's the mechanism for the first one. The second one, where we have HBr and a peroxide, which we'll draw on the next page. I'll add a page in here. If we have this same, and we add HBr and the peroxide to it, since we have the peroxide in there, we know it's going to be the initiator. So the peroxide is going to homolytically cleave to form two RO radicals. Okay, that RO radical is then in the first propagation step. The only thing it can react with, or the most reactive thing it can react with, is HBr. So it's going to abstract a hydrogen off of the HBr to form ROH along with the bromine radical. That bromine radical then can add into the alkene to form this tertiary radical. It's going to add to that carbon because the radical is electron poor, so you all want to form the most stable one. The most stable one is the most substituted one, and then that radical is going to go grab a hydrogen off of HBr, abstract a hydrogen to reform bromide, and give us our final product for the reaction, along with then we do a termination where any two free radicals, but the easy one is the two bromines coming back together to form Br2. Okay, and this is the termination step. With the in this reaction, it has one extra propagation step in it because we have to start with the RO radical, which is not incorporated into our final answer, and then we go from there. Okay, and that's just like the ones we've drawn before. Look it over and think about it as you're going along. Okay, you should be able to draw the mechanism for 2-methyl pentane reacting with bromine and light to form the 3-methyl 3-bromo pentane and HBr. It's a free radical. The bromine splits apart to form two of the bromide radicals. Then the bromine radical is going to pull off that most substituted hydrogen. Now, I always write these, as you have noticed, as a separate step instead of continuing them on, so that it makes it easier to see what happened each step along the way in this one. And then we'll abstract the bromine off of Br2 to form our product. Guess we formed the HBr there. And then we can bring two bromine radicals together to form Br2. And it's the same mechanism over and over and over. You form the radical, abstract a hydrogen, abstract the halogen, terminate the reaction. If you're starting with an alkane, they're always the exact same mechanism. So you know that mechanism, you won't have any problem with it ever again, say on the final at the end of class. So what can we do with an alkane? We've said two things we can do with an alkane. We can burn it to keep warm, or we can halogenate it. These are the only two things we can do really useful with an alkane. So the only one that's really useful synthetically is to brominate it, and we're going to brominate it on the most substituted carbon of the alkane. And then once we have the alkyl halide, we can either substitute for that alkyl halide with some nucleophile, either in well, never mind, we'll get to the types of substitution reactions in a minute, or we can eliminate it with a base, either a strong base or a weak base, to form the alkene. And then from both of these things we can carry on further to make many different things. So this chapter will really open up the possibilities to what we can do in this section, or in organic in general, and with the types of reactions we can do. So there are two basic mechanisms that we could think about something occurring. We could have the direct displacement, where the nucleophile comes in and attacks the carbon, kicking off the leaving group, giving us our substitution product along with the leaving group as an X minus, because the electrons went with it. Or the second way is we could see it as the leaving group leaves, we form a cation, and then the nucleophile adds to the cation to give us our product. So in this, we have to look at what's going on. In the first one, the SN2, the reaction is a direct displacement. The nucleophile comes in, we form a bond, kick out the leaving group. It happens all in one step. So we need to think about what type of reaction will be faster. What could we use in a SN2 to be faster versus in the SN1? What would be faster between the primary and the tertiary halide? So in the SN1, we have to form the cation. So which cation is more stable? Is it the more substituted one or the less substituted one? We know that from chapter 4, the more substituted the cation is, the more stable it is. So the T-butyl leaving group will be much faster in an SN1 mechanism because it's all about the formation of the cation. The SN2 is a direct displacement, so it's much better with smaller hydrogens out here, so the nucleophile can come in and form a bond to the carbon with the leaving group on it to kick it out all at the same time. Okay, so the primary is an SN2, the tertiary is an SN1 type mechanism. So can we draw a mechanism for the T-butyl chloride reacting with iodide in an SN1 type mechanism? So we need to kick the chlorine off, forming our cation, and then the iodide would react with that cation to form the alkyl iodide. So in this mechanism, we have two steps. So wherever our starting material energy level is to product, we're going to go over a big peak, level off, and then go over a much smaller one down to the products. So right here, need a different color, right here, where is the intermediate for the reaction. That intermediate is the cation. So our intermediate is this, along with the chloride, along with the iodide. So that's all what we have going on right there. Then we have our transition state, number 1, and our transition state, number 2. So transition state number 1 is what's going on in this step of our mechanism where the chloride is leaving. How do we go from T-butyl chloride to the cation? So we have to think of the second transition state, which we have drawn there with the second blue arrow. We're going from the cation to the final product of the alkyl iodide. So the other reaction here, the SN2, is the mechanism for it is the iodide comes in, displaces the chloride. It happens all in one step. So our starting material product is only going to go over one peak and down to the product. There's no any other steps because we only have one step in our mechanism. So we don't form any intermediates. We go directly from starting material to product. So in this is going to be our transition state for the reaction. So what's going on in that transition state? We are what can happen here where we have this carbon chlorine bond lengthening out. So as this is happening, we have the transition state for number 1, the first transition state, where the carbon-chlorine bond is lengthening out. We are forming a partial negative on the chlorine and a partial positive on the carbon, because we have to go from the neutral molecule, the T-butyl chloride, to the cation in this step of the mechanism. So we have to go from a chlorine with no charge to a chlorine with a negative charge, so it has to go through a partial negative, and we're going from a neutral carbon to the cation, so it has to have a partial positive as we're going over this transition state. Will look very similar, because now instead of breaking the bond between the carbon and the chloride, we are forming a bond between the carbon and the iodide. So the carbon has a partial positive, the iodide has a partial negative. It's going to look exactly like the transition state for the first one, because all we're doing is reversing the process we did. So here we're going from the cation and I minus to forming the bond to that carbon to give us the T-butyl iodide. Okay, so then I has a partial negative, the carbon has a partial positive, and we go from there. Okay, now right in on this SN1, so we keep track of them. Okay, so the SN2 reaction, we'll put 1. In the SN2, we have the iodide coming in and the chloride leaving all at the same time. So this carbon has the carbon chain on it, however many carbons it is, it doesn't matter. And then it's going to have the bond going out to the chloride. So this bond is breaking. The bond to the iodide is forming. Now, the charge on the chloride when it leaves is a negative. The charge on the iodide as it's coming in is a negative. So both of these are partial negatives. And the carbon is neutral because there are no positive charges in our mechanism. We go directly from the starting material, the alkyl chloride, to the alkyl iodide. So since the iodide is coming in with a negative and the chloride is leaving with a negative, they need to be on opposite sides of the molecule, so as far apart as possible. And then one hydrogen is going to be in the plane going straight back, and one hydrogen is in the plane coming towards us at the top of the transition state. So it's kind of planar between the hydrogen, the carbon, and that carbon of the first carbon of the R group. So that's how we have to spread everything out as far as possible for this. Okay, and we'll get into this more when we get into the reactions in a little bit after the SN. Okay, this page right here, okay, page 13, is very important. You have to know this material by the time we get to test 3. Okay, on test 3, it's all reactions, it's substitutions and eliminations. So we have SN2, SN1, E1, and E2. This page gives us a rough guideline on how we can decide what type of reaction it is. Okay, so in this page you will see multiple times in here, okay, as we go along. I've copied it a few times in both chapters 6 and 7, because it is so important to making sure we know, is it a substitution reaction or is it an elimination reaction? Right now we're down to they're all substitution reactions. We will cover elimination reactions in the next chapter. So this chapter is only substitution reactions, so we don't have to worry about all the things that say elimination on them. But read through here, think about what all it is asking or telling you, and make sure by the time the test rolls around, you know these things and know them well to be able to predict what's going to happen on the reaction. So here we have the SN2 mechanism, and we drew it already, where the nucleophile comes in, the leaving group leaves. It works best with the primary carbon because we want the smallest amount of steric hindrance around the carbon that the nucleophile has to come in to form a bond to. So on this bottom of this page, all that's going to happen in the mechanism is the hydroxide comes in, the bromide leaves, and we're going to form the 1-butanol, and every one of the reactions here is going to be the exact same mechanism. We just have to decide what is the nucleophile. So we have the sulfide, the methoxide, the cyanide. Now the cyanide, what can you draw the Lewis structure for that? Okay, we know that carbon has 4 electrons, nitrogen has 5 electrons, and the negative is 1. So even though it's written Cn minus, the carbon is the atom with the negative charge on it because it has 3 bonds and a lone pair. So the carbon's going to be the nucleophile to come in and attack the carbon with the bromine, kicking it off. And the next one, it's the acetylide that's going to come in, kick the bromine off. So we're going to have 4 plus 3 carbons with a triple bond in there, with the triple bond carbon bonded to the carbon of the CH2. The next one is the carboxylate. So we're going to make the ester. And the last one, the nucleophile, is the nitrogen. So we're going to get the trimethyl ammonium salt out of that. Okay, but the mechanism for all 7 of these is exactly the same. The most important thing is knowing where are the electrons that can act as the nucleophile. So be careful about that as you're going along, that you think about what is nucleophilic and what we... Oops. So there are 2 types of problems you will see on this test. Okay, one is where I give you the starting materials like this first one, and you decide what it's going to form. So in it, we have to follow these steps to figure out what can happen. The first thing we want to do is identify the functional group classes and go from there on down. So we have the alkylamine and we have the methyl iodide. Are there any leaving groups? What is a leaving group? We talked about in class. I haven't said it in here yet, but the leaving groups are all things that can leave as a weak base. So chloride, bromide, and iodide are some of the best leaving groups because we all know HCl, HBr, and HI are strong acids. Strong acids have weak conjugate bases, so Cl minus, Br minus, I minus would all make a good leaving group. So then, do we have any bases or acids? We have the amine. It's a weaker base, not a strong base. And the electrophile would be the methyl iodide, and the nucleophile would be the amine. And there are no strong acids or strong bases, so a proton transfer isn't the first step. So all we can do is have our nitrogen attack the carbon, kicking out the iodide to give us the nitrogen with now 4 bonds to it with a positive charge on it, and the iodide would be the counter ion to it. Okay, so that's the type of thing we'll do if we have to predict what the product is for the reaction. Okay, and there will be a number of those on the test. Every test will have a number of those of the type of reactions we're talking about on that section. Okay, so be careful, you know what type of reactions we've talked about in that section on the test to know what type of possible reactions there are. The next one here is we have the starting material, we're given the product. What do we need to add to make that happen? So in this, we have to look for where are these 2 carbons in our product. Okay, check the connectivities. These 2 carbons are these 2 here, so we need to form this bond between the ethyl group and the other chunk. Okay, the ethyl group, identify the product, do a retrosynthetic analysis, see which bond you have to form. Think about what the nucleophile could be or the electrophile. We're starting with an ethyl bromide. We know it's got the leaving group on it. So the nucleophile is just going to be the other half of the molecule with a negative charge on it. So it's just going to be this, where we do an SN2 on the ethyl bromide to form the product. That's all. Okay. In the next one, we see an ethyl group again. It's going to be these two carbons here, so we're going to have to form the bond between the acetylenic carbon and the CH2 of the ethyl group. So all of this crap stuff is going to, the methyl acetylene is going to have a negative charge on it, so it can be a good nucleophile to form that bond to the ethyl of the ethyl bromide. Okay, so it's also an SN2 because all we have is the primary bromide. Anytime it's primary, it's going to be an SN2. It's not going to be a SN1 because you can't form the primary cation. In this last one, if all of the carbons have to come from ethyl bromide, it's going to take more than one step. Sorry, we need to form somehow ethanol because we need to get an oxygen on it. So we're going to add hydroxide to the ethyl bromide. It'll do an SN2 to make the ethanol. Then the ethanol we're going to have to turn into a good nucleophile. How can we remove the hydrogen off of ethanol? What would we use to pull off that hydrogen on every one of the ethanols in the molecule to form the alkoxide, which then we could add to another equivalent of ethyl bromide to form the diethyl ether? The only way we can remove that hydrogen is to add a base that is stronger than the product of the reaction to make sure it pushes it all the way to the right. So we need to go to the left one atom from oxygen over to nitrogen in the periodic table. NH2 minus would be much stronger of a base than ethoxide, so we could use NH2 minus to pull off that hydrogen to form the ethoxide, and then the ethoxide react with ethyl bromide to form our product. Whoops, what'd I do? Okay. So in an SN2 reaction, we talked about it being a direct displacement going on at one time. So the nucleophile is coming in, just like we drew earlier. The nucleophile is coming in as the leaving group leaves, so they have to be on opposite sides of the molecule, just like they're shown here, circled in red. Okay, so if we have a stereocenter, and this is the important part of this section, okay, if we have a stereocenter in an SN2 and do an SN2 reaction to it, if we look at this reaction here, the bromide is highest priority, then the ethyl, then the methyl. This one is R for our stereocenter. If we take this R, alkyl bromide, and do an SN2 displacement on it with the sulfide, okay, we now look at it, and it's going to go from the sulfide to the ethyl to the methyl. Now it's going counterclockwise. Our product is S. So in this reaction, in an SN2 reaction, if you have a stereocenter, the stereochemistry is inverted going from starting material to product in that. But that's only if you have a stereocenter in your starting material. Okay, so be careful about that. Don't make a stereocenter, but if you have one, you have to show that the product inverts in the reaction. And it's like if you're walking out in the rain and you have an umbrella and the wind catches the umbrella and it flips over. That's the sort of thing that's happening here, because it's going from the leaving group on the right side of the carbon to having the nucleophile added from the left side. Okay, so if that doesn't make sense, look it over, come in and talk to me or send me an email, and we can talk about that as we're going along. But it's all about what happens in the transition state for this reaction. We need to form, so the SN1 mechanism, in the SN1 mechanism, the leaving group leaves, we form the cation, and then whatever the nucleophile adds, forming our product. So we go through the cation is sp2 hybridized, trigonal planar. So it's flat. The nucleophile can add from either side, and it doesn't matter. So in this first one, the chloride's going to leave. We're going to form our cation, and then the iodide's going to add, and we're going to make the 2-iodo-2-methyl butane. Okay, there is no stereochemistry because we didn't start with any stereochemistry. We don't have to worry about that in this case. Okay, and the second one, the chlorine leaves. We form the cation, and then the methanol adds to that cation to form the protonated ether. And then another equivalent of methanol comes in to grab the extra hydrogen to give us our methyl ether. Okay, and in every SN1 mechanism, we have to form the cation. We cannot do it without the cation. If you do not show this step in your reaction, it's wrong if it's an SN1 mechanism. So make sure you always show that cation in the mechanism and go from there as you're going along. So if we had a stereocenter in an SN1 reaction, we know the cation is trigonal planar. So it's flat. The nucleophile can add from either side, and it will add from either side. It can add from the front side or the back side. And down here at the bottom, we have a compound which is bromines 1, propyls 2, ethyls 3. It is S. It goes through that planar cation. The cation, the nucleophile can add from either side, and it will. So we're going to get both the S and the R product out of it in roughly a 50-50 mix. Okay, so if you have an SN1 reagent with a stereocenter, the last thing you want to do is undergo, or if you have a tertiary stereocenter, the last thing you want to do is undergo an SN1 mechanism because the stereocenter is lost in that reaction. So here we have how to describe what's going on in these both in the mechanism. In an SN2, I'm going to blow it up on this page. We can talk about each one. We have the direct displacement. The rate determining step is the only step in the mechanism if there's a good leaving group. The rate is equal to the concentration of both the substrate and the nucleophile. So if you double one of those two, you double the rate of the reaction. If you double them both, you quadruple the rate of the reaction. Okay, the reaction rate, methyl is the fastest. The tertiary is not going to happen in an SN2. And the stereochemistry, it undergoes an inversion of configuration if there is a stereocenter because it is a direct displacement. Nucleophile comes in from the backside, leaving group leaves all at once. Okay. In the other one, the SN1 reaction, we have the rate determining step is the loss of the leaving group. So the first step, so the rate of the reaction is only equal to the concentration of the substrate, and the solvent doesn't matter. The nucleophile doesn't matter. And the rate of these reactions is tertiary is the fastest, on down to secondary, primary, and the methyl. And methyl's not going to happen. You're not going to form the methyl cation. You're really not going to form the primary cation. And the racemization of the configuration is what happens to a stereocenter if you have it. Okay, so think about this page. Make sure you understand what it's implying and what's going on in the mechanism of both for what's happening. Okay. So drawing a complete mechanism, we have to think about what we have and what can go on. If we have, and there are only a couple of steps to any reaction in organic that has an ionic, cations and anions, nucleophiles and electrophile type mechanism. So we have a good leaving group. The leaving group leaves, forming the cation, loss of a leaving group. The nucleophile attacks, nucleophilic attack. Then, once we have the protonated ether, It's a proton transfer where methanol comes in, grabs the extra hydrogen, and we get the methyl T-butyl ether. Okay, so this mechanism would have 3 steps because the nucleophile we add in is not a methoxide, MEO minus, it's a neutral methanol. So it adds in as the neutral methanol, forming the protonated ether, and then you have to remove the extra hydrogen with another equivalent of methanol because of Le Chatelier's principle. So that's going to be the mechanism if you don't have a negative charge in the nucleophile, in the solvent. You're not going to in an SN1. Okay, it's normally going to be 3 steps at least. Here we have just the opposite side of things where we add hydrochloric acid. So the first step to the T-butanol, the OH is not a good leaving group because if it left, it'd leave as a hydroxide. Hydroxide is a strong base. Strong bases are not good leaving groups. So we need to protonate it first, do a proton transfer, and then water leave, you form the OH2 plus, a good leaving group. The water leaves, forming the cation, loss of the leaving group, and then nucleophilic attack to give us our final product for the reaction. Okay, just to add a little bit of fun to the reaction, in this case we have a secondary bromide, but next to it we have a quaternary center, a carbon with 4 carbons off of it. So the loss of the leaving group forms that secondary cation. We all know that secondary cations are not as stable as tertiary cations. So what can happen is one of these groups over here can take its electrons and migrate over to form a new cation. So we have a carbocation rearrangement. So we go from 3 methyls on one carbon to 2 and 2 with a positive charge on the carbon that had the 3 methyls. And then the nucleophile can add in the nucleophilic attack to give us this, a compound with a rearranged alkyl skeleton in it. And this happens anytime the cation is not the most substituted cation that you can form in that molecule. So there will be 1 or 2 of these on the test. There's some of them in the homework, online, on active. They're all, you'll see a bunch of these. Be careful, don't forget about them, okay? The next page, we have drawing the complete mechanism for an SN2. In this one, we don't have a strong nucleophile, we have a weak nucleophile. So the methanol would come in, displace the bromide to form the protonated ether. So the nucleophilic attack and the loss of the leaving group happens because we have to show 2 arrows. And then methanol will come in to grab the extra hydrogen to form the methyl ether along with the protonated methanol as a side product. Do you have to draw this in the reaction? No. All I'm looking for is the 1-methoxybutane or methyl N-butyl ether. Okay, you don't have to draw all the side products. If they help you, draw them all in, keep track of them, but you do not have to draw them for your answer on the test. So here we have sodium bromide and sulfuric acid that we're adding to 1-butanol. The butanol is not a good leaving group, so we have to proton transfer first to turn it into water to make it a good leaving group. And then the sodium bromide can come in and do an SN2 on it and have the nucleophilic attack and the loss of the leaving group going on. With it being a primary carbon, we know it needs to be a SN2 so you don't form the cation. You don't want to form a cation on a primary carbon. That's bad. Bad, bad, bad. Don't do that. Okay? Here we have an epoxide, and in the epoxide, if we were given going from the 3-membered ring to the 1,2-diol of our product, we see we have to break a bond to that initial oxygen. So we're going to have to proton transfer to make it a good leaving group. So we protonate the epoxide, and then the water nucleophile adds into the carbon with the leaving group on it, so it adds to one side of the epoxide, it doesn't matter which, kicks off the OH plus, so we have nucleophilic attack and the loss of a leaving group all going on in that SN2 attack. And then we have the proton transfer to remove that extra hydrogen off of our oxygen to give us the ethylene glycol. Okay, so in this one, and proton transfers are easy, that you'll see those a lot in these mechanisms, so keep track of where they are and what has to happen. Here again is that page I said you need to know. Okay, read through it. Hopefully you know most of it by now, but in summary, methyl and primary substrates favor an SN2, tertiary substrates favor an SN1, secondary allylic and benzylic substrates can go either way depending on what kind of conditions we have in the reaction. And vinyl and aryl substrates, vinyl would be a double bond with a leaving group, and an aryl is an aromatic ring with a leaving group on it. Those do not react via this mechanism, period. Either one, because we can't form the cation and we can't do the direct displacement. Okay, allylic substrates are, as we said, where we have a CH2 or a carbon with hydrogens on it on the carbon connected to the double bond. And benzylic, we have said in the past, is an aromatic ring with a CH2 or a carbon with hydrogens off of it and a leaving group off of it. Those two cations we can easily form, and we can show with resonance structures them moving around. So leaving groups, we've talked about them. Leaving groups are the conjugate base of a strong acid. So these down here are the strong acids. So these here could make decent leaving groups in that. Okay, so think about that as you're going along. A good leaving group has to be the conjugate base of a strong acid. It has to be neutral, or not neutral, it has to be stable on its own to be in the reaction without anything hooked to it. You can't kick out a strong base because strong bases aren't stable on their own. So the good leaving groups, the halides, iodide, bromide, chloride, the sulfonate, okay, a generic one with just some R group. It doesn't matter what that R group is. One example of it is a tosylate here, where it's a paratoluene sulfonate for the reaction. Okay, polar protic solvents favor SN1. Examples of polar protic are water, alcohols, acids, amines, things that are both polar, which you know what that means. It's got a bond between a more electronegative atom and a hydrogen, and it has, well, the protic has a hydrogen that's bonded to that more electronegative atom. Polar aprotic are polar molecules where the polar bond is not connected to a hydrogen. Okay, so DMSO, acetonitrile, DMF, HMPA, those are all polar aprotic solvents, and they favor the SN2 reactions. Okay. So, summary of the reactions. If we had a secondary bromide and we added sodium sulfide, ignore the sodium, write in the negative. We have DMSO. DMSO favors an SN2. Since it's a secondary leaving group, it could be either SN2 or SN1, so we have to decide what can happen. Okay, this nucleophile, HS minus, is a good nucleophile, so that leans more towards SN2. You got the negative charge on the sulfur. Okay, the sodium is the cation, and the counterion is not important to this reaction. So anytime you have that counterion, go ahead and scratch it off, ignore it, just think about the thing with the negative charge. Okay, the leaving group is bromide, so it's a good leaving group, so it doesn't favor SN2 or SN1, and the solvent DMSO, being a polar aprotic solvent, favors SN2. So this reaction would be an SN2 where the sulfide comes in, kicks off the bromide, and you get an inversion of configuration where this is R, so this one has to be S. Okay, because in an SN2 mechanism, if you have a stereocenter, it is inverted. So basic nucleophiles, we can make an ester, we can make a nitrile, we can make a thiol, we can make an alcohol, we can make an ether, okay, just by adding whatever nucleophile we need to our R group, whether it's SN1 or SN2. So there's the reactions: the cyanide, sulfide, hydroxide, methoxide, or alkoxide does an SN2 if it's a secondary, and these wouldn't do it SN1 very well because they're stronger bases. But they'd work very well for SN2s. Okay, so next page has one last one. You can make the alkyl halide. Here's all the information again for substitutions. You need to know this. So this is 3 times we've had it in here. Make sure you know that before we go on, okay, before we get to the test in early November, okay. And if you have any questions about anything, make sure you send me an email and ask about it as we're going along. So can you draw the mechanism for methoxide reacting with the iodide? Since it's a primary leaving group, it's got to be an SN2. In the second one, it's a tertiary leaving group with a weak base. So we form the cation, then methanol adds. And then the methanol will come grab the extra hydrogen to give us our final ether. So we'll have that for our product. Okay, so we have the SN2 direct displacement, the SN1 that's the tertiary leaving group with the weak base, weak nucleophile. The second one is going to be an SN2 because we have the strong base and the good leaving group. This one's going to be a 1 mechanism because we have the tertiary carbon form the cation, add the methanol in to form the protonated ether, and then take off the extra hydrogen to give us our final ether. So here we have some problems to make it a little harder. In the first one, we don't have a strong leaving group. We don't have any, all we have is an acidic hydrogen and a strong base. So we're going to, in the first step, remove the hydrogen off of the phenol to make the phenoxide, and then the phenoxide would react with the propyl bromide in an SN2, and we'd end up forming the ether out of that. Okay, the next one would be an SN2. Then the last one, sodium cyanide, is just Cn minus. It's an SN2. So we're going to get the iodocyclohexane, the nitrile adding on to the 6-carbon chain. Be careful about counting how many carbons you have. And then the middle one here is going to be the ether, where the leaving group leaves, forming the cation. Methanol adds to it, forming the protonated ether. And then take off the extra hydrogen to get us to our product. You don't have to draw a mechanism for these. I'm showing the mechanism so you have it for studying going forward. Okay, then how would you do these where it's asking what kind of reagents do you need? In the first one, we're taking a hydrogen off of a nitrogen, so we need a really strong base. So 1 column to the left of nitrogen is carbon. So CH3 minus would remove the hydrogen of the aniline to make the analyde. And then we just need to do an SN2 with that analyde. pen died. So we finished the SN2 with the bromide leaving. That gives us the propyl anilide. In the next one, we look, the carbon chain is the same number of carbons. All we're going is to an alkene, so we would have to remove a hydrogen off of the adjacent carbon of the bromine to do an elimination. We haven't talked about eliminations, but since it's here, we'll draw it in. It'd just be a strong base, grabbing the hydrogen, forming the double bond, kicking out the bromine, and we get the alkene. And the next one we see where we have to form the bond to a methylacetylene. So all we're going to have is the methyl acetylide ion coming in, doing the SN2 on the bromide to give us the product. And we have that. And I think this is the end of this section. Oh, not quite. Got one more nucleophile electrophile problem like what we have done in class. If we look at what changes, the nucleophile grabs a hydrogen to form the negative charge. Then we have a resonance structure based on the resonance arrow with the arrowheads on each side. Then we have another resonance arrow with the arrowheads on each side, sending the electrons back down. Then we have the nucleophile and electrophile. Nucleophile attacks the carbon, sends the electrons up to the oxygen. Then nucleophile negative, electrophile the hydrogen, protonate the OH, and then finally we see we have to grab a hydrogen, form a double bond, kick off hydroxide, and there we are, nucleophile, electrophile. And then the last one, draw a mechanism for each of the following reactions. So the second one is going to be just an SN2. It's easy. The first one, should have put more space in the page. But we have that and HBr. So we don't have a good leaving group, so we need to protonate it to make a good leaving group. Make the water it can leave, forming the cation. And then the bromide adds to the cation to form the product. Okay, so the first one is an SN1, the second one is an SN2. Okay, the second one we have the strong base, strong nucleophile with the methoxide, so it has to be a 2 mechanism. The first one we don't have a strong base, so, and it's a tertiary leaving group, so it has to be a 1.